Welcome back, listener. Today, we're going to be taking a deep dive into something pretty fascinating.
Oh, yeah.
Um, it might sound a little bit scary at first,
Yeah.
but we're going to be talking about how things break.
Okay.
So we're going to be looking at material failure.
Uh,
And,
Sounds good.
you might be thinking like,
Yeah.
okay, well, I use things every day.
Yeah.
How does this affect me?
Right.
But, understanding how materials fail can actually
Yeah.
help you make better decisions as a consumer.
Absolutely.
About the products you choose, the
Yeah.
things that you see around you, and, even help you recognize potential risks in your environment.
Yeah, totally.
So we're going to be looking specifically
Yeah.
at excerpts from a material science textbook
All right.
to kind of get to the core of it all.
Okay.
And that would be
Right.
fracture, fatigue, and creep.
Okay.
Those are kind of the big three
Yeah.
we'll be talking about.
Right.
Um, so to help us decipher all of this, we have our expert here with us.
Absolutely.
Are you ready to kind of shed some light on these tiny flaws that can cause big problems?
Yeah, I think the best place to start is really just by understanding like the two main ways
Yeah.
that things actually break.
Right.
So you have your ductile fracture
Okay.
and you have your brittle fracture.
Right.
Ductile fracture, you can imagine like a piece of chewing gum.
Okay.
So you pull it and it stretches and stretches and stretches, and then finally it snaps.
Okay.
Brittle fracture is like a dry twig.
Gotcha.
You just snap it and it just breaks.
Right.
There's very little warning, very little deformation.
So like a dramatic versus a subdued breakup.
Right.
What dictates whether something is going to go that
Yeah.
chewing gum route versus the twig route?
So that's really interesting because when you look at materials,
Yeah.
even the toughest materials, right?
Yeah.
They have microscopic flaws,
Oh, wow.
tiny little cracks. And these cracks, they act like stress amplifiers.
Okay.
So you can imagine like a tiny little notch,
Yeah.
and the force is being concentrated at that notch, and it makes the material much weaker in that region
Okay.
than it should be.
I see.
And those flaws can really determine whether something is going to undergo ductile or brittle fracture.
The textbook actually has a great example
Oh, yeah.
to illustrate this, and this is something I think we can all relate to.
Okay.
It's those like plastic packages
Yeah.
that are like impossible to open sometimes.
Oh, yeah, you got to get the scissors out.
Yes, exactly. You have to get the scissors.
Yeah.
And it says like if you just make a small little cut
Right.
at the edge of that package,
Yeah.
it's so much easier to just tear it open.
Absolutely.
So it's kind of like those stress concentrations
Right.
in action.
Those flaws are being exploited when you make that little cut.
Yeah, it's like
Yeah.
a little cheat code
Yeah, totally.
to opening those packages.
Right.
But, thinking about this on a larger scale,
Yeah.
like if we scale this up to something like bridges or airplanes,
Yeah, right.
these things that are
Yeah.
supposed to be so,
Yeah.
strong and
Uh-huh.
unbreakable, really.
Right.
But they have those tiny little flaws too
I do.
that we can't even see
After.
with the naked eye.
Right.
And especially when they're exposed to like repeated stress over time,
Yeah.
those little flaws can actually
Man.
compromise the strength and lead to some failures.
Yeah.
So those microscopic flaws can actually have a huge impact.
Yeah.
And speaking of repeated stress,
Yeah.
that brings us to fatigue, right?
Yeah, exactly.
Yeah.
Fatigue is basically the weakening of a material
Okay.
due to repeated stress cycles.
All right.
So you can think about it like bending a paperclip back and forth until it breaks.
Okay. So it gets tired
It gets tired.
after being bent back and forth so many times.
Exactly.
But in the case of like,
Yeah.
bridges and airplanes and things like that,
Uh-huh.
tired can actually mean like a sudden and catastrophic failure.
Right. Exactly.
So it's not something to take lightly.
No, not at all.
And what's interesting is that fatigue can actually occur
Yeah.
at stress levels that are way below the material's yield strength,
Absolutely.
especially if it's like a fluctuating or like a cyclic stress.
Yes. Especially when those stresses are changing over time.
So it's not just about how strong the material is,
Yeah.
but how it handles those repeated stresses.
Right. It's like you said, like a marathon runner versus a sprinter.
Yeah, exactly.
Different types of strengths.
Right.
Absolutely.
Yeah. The textbook actually shows an image of a fractured steel shaft,
Okay.
and it has these like markings on it called beach marks.
Yeah, beach marks are really interesting.
Yeah.
Because they actually tell the story of that crack growing.
So each beach mark
Uh-huh.
is like a timestamp.
It is.
Like this is where the crack was at this point.
Yeah, you can actually see the progression of the failure over time.
Wow. That's incredible.
It is. And if you look even closer under a microscope,
Yeah.
you can see even tinier markings
Oh, wow.
called striations.
Striation.
Yeah, and those form with each stress cycle.
Oh, so it's even.
It's a very detailed history of the stress that material's been through.
Wow. So you can really glean a lot of information
Look again.
just by examining
Yeah.
how something broke.
It's like a forensic investigation at the microscopic level.
Yeah, exactly.
Yeah.
But knowing how these failures happen,
Uh-huh.
is there anything we can do to prevent them?
Yeah, absolutely. So the textbook actually highlights a couple of different strategies.
All
Some of them involve like really clever design choices,
Okay.
like rounding sharp corners to minimize stress concentrations.
Right.
Instead of having like a 90-degree angle,
Yeah.
you make it like a nice smooth curve.
Yeah, so you're kind of streamlining the design
Yeah, exactly.
in a way to kind of reduce those
Right.
stress
Yes.
hotspots.
Reduce those areas where the stress is going to concentrate.
Yeah.
And then you have things like surface treatments,
Okay.
like shot peening.
Shot peening's a really cool process.
Yes.
What is that?
You're basically bombarding the surface with tiny little beads
Okay.
to create compressive stresses in the surface.
What does that do?
And that actually makes the material more resistant to crack formation.
So it's kind of like giving it a protective shield
That's a great analogy, yeah.
to kind of deflect those stresses.
Exactly.
All right, and then there's creep.
Creep.
Now, creep, the name itself,
Yeah.
sounds a little
It does sound a little unsettling.
unsettling.
A little creepy.
Right. Almost like something out of a horror movie.
It is a bit of a horror story for engineers.
Yeah.
But creep is this slow,
Okay.
gradual deformation.
So it's not like that sudden snap.
Not a sudden snap. This is like a long, slow process that
Right.
happens over time.
Right.
So you can imagine like a metal beam
Yeah.
that's under a constant load.
Okay.
And over many, many years, it slowly starts to sag
Okay.
under its own weight.
I see.
That's creep.
So it's almost insidious in a way. Yeah.
It's insidious, it's slow,
Yeah.
and it's very difficult to predict sometimes.
The textbook mentions this
Yeah.
S590 alloy,
Yeah, that's a good.
and it shows how the time to rupture,
Mm-hmm.
like how long it takes for it to actually break,
Mm.
decreases dramatically
yes.
as the temperature goes up.
Absolutely.
So it's like heat really
Heat is a big factor in.
really accelerates that creep process.
It does, and that's why, like jet engines and power plants,
Right.
things that operate at very high temperatures,
They have to really,
they have to consider creep very carefully.
yeah, you have to make sure that your materials can withstand those
Exactly.
extreme conditions.
Absolutely.
And predicting creep can be really tricky.
It can be.
So engineers have come up with a method called
Yeah.
the Larson-Miller parameter.
The Larson-Miller parameter is a very clever way to extrapolate data
Okay.
from short-term tests to make long-term predictions.
So it's kind of like having a
It's like a crystal ball for materials.
crystal ball
Yeah.
for creep.
It just see into the future.
That's pretty cool.
It is.
But going back to brittle fracture for a second.
Yeah.
The textbook mentions that those microscopic flaws
Mhm.
we talked about earlier, they're not the only culprits.
No, they're not.
Even like bigger
Right.
defects can play a role, like voids.
Macroscopic defects.
Yeah, microscopic defects,
Yeah.
like voids, inclusions, or even sharp corners.
Right. Those can all act as stress concentrators,
Gotcha.
and they can make a material more susceptible to brittle fracture.
And this is where this idea of fracture mechanics comes in.
Yeah, fracture mechanics is a really important field for
Yep.
understanding how materials break.
What is that exactly?
It looks at the relationship between stress levels,
Okay.
material properties, and those flaws.
Okay.
And it tries to quantify the risk of fracture.
Okay.
So basically, how likely is it that this material is going to break,
Gotcha.
given a certain crack size and a certain stress level?
So it's like having a set of tools to predict and hopefully prevent,
Yeah.
like a brittle fracture disaster.
It's a way to design safer structures
Okay.
by understanding how those cracks are going to behave.
And one of the key concepts here is fracture toughness.
Fracture toughness is really important.
What is that?
So fracture toughness is denoted by Kc,
KC. Okay.
and it's a material property
Right.
that tells us how resistant a material is to brittle fracture
Okay.
when a crack is already present.
I see.
So it's basically like how much punishment
Yeah.
can that material take before it completely fails?
So a material with like a high fracture toughness
Mm-hmm.
can withstand a bigger crack
Exactly.
before it fails completely.
Yeah, it's a tougher material.
That's reassuring.
It is.
But how do we actually measure this?
So we use standardized tests
Okay.
to measure fracture toughness.
What kind of tests?
And they can be quite complex, but
Yeah.
essentially you prepare a specimen
Okay.
with a pre-existing crack, and then you load it until it fractures.
Okay.
And by measuring the load
Okay.
and the crack displacement,
Yep.
you can determine this value called key IC,
Key eye.
which represents the material's fracture toughness
Okay.
under plane strain conditions.
Plane strain.
Yeah.
What is that?
It's a bit of a technical term,
Okay.
but basically it means that the material around a crack
Yeah.
is constrained
Okay.
from deforming in a certain direction,
Okay.
which actually makes the crack more likely to propagate.
I see.
So key IC is kind of like a worst-case scenario
Yeah.
measure of fracture toughness.
Okay.
It's showing us how the material behaves
Yeah.
under these really challenging conditions.
So it's really testing its resilience
it is.
under pressure.
Yeah.
The textbook also talks about impact testing.
Impact testing.
So like the Charpy and the IZOD tests?
Yes.
And
Those are classic impact tests.
What do they tell us?
So they don't give us a precise fracture toughness value
Okay.
like key E,
Okay.
but they give us really valuable insights
Oh.
into a material's tendency to fracture
Okay.
in a brittle or a ductile manner,
Okay.
especially at different temperatures.
So it's like seeing how the
It
material
reacts.
putting it through a...
Under pressure, literally.
Yeah, exactly.
And this leads us to this concept of the ductile to brittle transition.
The ductile to brittle transition.
So this is where a material that's normally ductile
Uh-huh.
can suddenly become brittle
Right.
and prone to that catastrophic failure.
Like those World War II ships that fractured in the cold water.
Yeah, exactly.
That was a classic example
Wow.
of the ductile to brittle transition.
So these impact tests help us determine whether a material
Okay.
exhibits this transition and at what temperature range
Exactly.
it happens.
And that's really important for materials that are used in cold environments,
Right.
where that risk of brittle fracture,
It's much higher.
it's like a warning system
It is.
telling us when a material might become susceptible
Yeah.
to that sudden,
It is.
unexpected failure.
And by understanding that transition engineers can then select materials that are safe to use
Right.
at their intended operating temperature.
So it's not just about choosing the right material.
No.
It's about understanding
It's about understanding how that material is going to behave
Yeah.
under different conditions.
how temperature
Absolutely.
affects its behavior.
Yeah,
Wow, that's a lot to digest.
it is.
But we've covered some really
Yeah.
important ground here.
We've gone from those tiny invisible flaws
Right.
to macroscopic cracks.
Yeah.
Explored this concept of fracture toughness,
Mhm.
delved into this fascinating world of impact testing
Yeah.
and the ductile to brittle transition.
It's amazing how much we can learn
It is.
just by understanding how things break.
Absolutely.
Are you ready to delve deeper into the world of fatigue?
I am. Bring it on.
All right, let's do it.
Oh, yeah. Fatigue is a sneaky one.
Yeah, it is. It's like it kind of creeps up on you.
It does. It's like a thief in the night.
Yeah. And before you know it, something's broken.
Right, exactly. And what's really interesting about fatigue is that it can happen
Yeah.
at stress levels that are way below
Sure.
the material's yield strength.
So it doesn't even have to be like super strong.
No, not at all, especially when those stresses are fluctuating or cyclic.
Okay, so it's like you said, it's that repeated stress.
It's that repeated stress over time that really wears the material down.
So it's not just about how strong it is, it's about how it can handle
Exactly.
that repeated stress over and over again.
It's like that endurance.
Yeah.
It's that fatigue strength.
Right, exactly.
So the textbook actually describes
Yeah.
3 main types of cyclic stresses.
Okay, what are those?
You have reverse stress,
Okay,
you have repeated stress,
all right.
and then you have random stress.
Okay, so 3 different flavors.
3 different flavors of cyclic stress. Yeah.
Well, let's break those down.
Okay, so reverse stress.
Yeah.
You can think about it like a perfectly symmetrical wave.
Okay.
So it goes from maximum tension to maximum compression, and those forces are equal in magnitude.
Okay, so it's like a spring being stretched and compressed.
Exactly, like a spring bouncing up and down.
Okay,
Yeah.
gotcha.
So that's your reverse stress.
All right, what about repeated stress?
Repeated stress is a little bit different.
Okay,
It's asymmetrical.
okay,
So the maximum and minimum stresses aren't equal.
okay.
So think about like a bridge
Yeah,
that experiences higher stresses when traffic is heavy
okay.
and lower stresses when there are fewer cars on it.
So it's not like a perfect up and down.
No, it's more like
It's a little bit uneven.
it's uneven. Yeah, it's like a seesaw with unequal weights on either side.
Yeah, gotcha. Okay, and then we have random.
Random.
Stress cycling.
Random is the most chaotic of the three.
Okay.
So the stresses are varying irregularly, both in amplitude and frequency.
So it's like completely unpredictable.
It's unpredictable, yeah.
Okay.
Think about like a component in a car engine.
Yeah.
It's subjected to all sorts of different stresses.
Right, as the engine speed changes?
Yeah, as the car accelerates, decelerates.
As you're hitting bumps and things.
Exactly. It's a very complex stress state.
So how do engineers make sense of all of this?
So they've come up with ways to quantify these cyclic stresses.
Okay.
Using a few key parameters.
Right.
You have your mean stress.
Okay.
You have your stress range.
Right.
And you have your stress amplitude.
Okay, so we're basically breaking this down.
Yeah, we're trying to simplify this very complex.
They're like measurable pieces.
Into measurable pieces, exactly.
Right, so let's define those then.
Okay, so mean stress.
Yeah.
That's like the average stress over a complete cycle.
Right, so if you're looking at that wave, it's kind of like that middle point.
It's like the average height
of
a mountain range. Yeah.
Gotcha.
And then you have stress range.
Stress range.
Which is the difference between the maximum and minimum stresses.
Okay, so that's like measuring from the highest peak
to
the lowest valley?
Yes, exactly.
Okay.
And then stress amplitude is simply half the stress range.
Okay.
So it represents how much the stress fluctuates.
Yeah.
Above or below that mean stress.
Okay.
Yeah.
So we're basically getting a feel for like
we're characterizing
the intensity of those.
How intense those stresses are,
Okay.
Exactly.
How do we actually test a material's ability to withstand fatigue then?
So one common method is the rotating bending test.
Rotating bending test.
Yeah, it's a pretty cool test.
What is that?
You basically take a specimen
Okay.
and you subject it to alternating tension and compression stresses
Okay.
while rotating it.
While rotating it.
Yeah, so it's like spinning.
So it's like a really intense workout for the material.
It's a workout for the material.
Okay.
Yeah.
And what does that tell us?
So the results of this test are plotted on what's called an SN curve.
SN curve. Okay.
Yeah, so S stands for stress amplitude.
Okay.
And N stands for the number of cycles to failure.
So it's basically telling us...
It's telling us how many cycles.
At a certain stress level.
At a certain stress level, yeah.
The material can withstand.
Exactly. It's like a map of the material's fatigue endurance.
Gotcha.
And there are different types of SN curves.
Okay.
Some materials, like certain steels, they have what's called a fatigue limit.
Fatigue limit. What's that?
So that's a stress level below which they can theoretically withstand an infinite number of cycles.
So it's like they have this built-in safety net.
It's like a threshold below which they're not going to fail.
No matter how many times.
No matter how many times you cycle them.
You stress them out.
As long as the stress stays below that limit, they're good.
That's pretty impressive.
It is. It's a very desirable property for certain applications.
But what about materials that don't have that?
So a lot of materials like aluminum alloys, copper alloys, they don't have a fatigue limit.
Okay.
Their SN curves just keep decreasing.
So they will eventually fail.
They will eventually fail.
No matter what.
It's just a matter of time.
Okay.
Yeah.
And that's where fatigue strength comes in, right?
Exactly. So fatigue strength is the stress level that will cause failure at a specific number of cycles.
All right.
Typically 10 to the 7th power cycles.
Okay, so we're talking a lot of cycles here.
A lot of cycles,
So it's like we're trying to quantify...
Yeah, we're trying to get a
sense of...
It's going to last.
How long it's going to last.
Yeah.
Under these cyclic stresses.
But the textbook mentions that fatigue data can be a bit messy.
It can be. Yeah, fatigue is...
Why is that?
It's influenced by so many factors.
Okay, like what?
You have material variations.
Right.
You have surface condition.
Okay. The environment that the material is in.
Okay.
All of these things can affect.
So it's not just about the material itself.
No, it's about the whole system.
It's about everything that's acting on it.
Yeah, and those SN curves.
Yeah.
They often represent average values.
Okay.
And there's always some degree of uncertainty.
So it's like we're trying to predict the weather.
Exactly. It's like predicting the weather.
You can use all the data you have.
You can.
But there's always those...
There's always those unknowns.
Unknown variables.
Yeah.
Okay, so let's talk about how these fatigue cracks actually form.
So fatigue cracks almost always start at the surface.
At the surface.
Yeah, and often at points of stress concentration.
Okay.
So remember those microscopic flaws and macroscopic defects?
Right, like those little scratches.
Scratches, sharp corners.
Yeah.
The threads on a bolt.
Okay.
All of those things can act as stress amplifiers.
And those are all on the surface?
They are.
Okay.
And they make those areas more vulnerable. to cracking.
So it's kind of like the weakest link in the chain.
It is. It's the weakest link.
That's where the crack's going to start.
That's where it's going to start, yeah.
Okay.
And once that crack initiates, it starts to propagate with each stress cycle.
Okay, so it gets bigger and bigger.
Bigger and bigger. Yeah.
And that's where we see those beach marks and striations.
Exactly. Those are the telltale signs of fatigue failure.
Yeah, it's like the material's last will and testament.
It is. It's telling the story.
Revealing the story.
Of its demise.
Of how it died.
Yeah.
But if we know how these cracks form and grow, can we do anything to prevent them in the first place?
Absolutely. So there are several strategies we can use to enhance a material's fatigue resistance.
Or like what?
So we talked about design.
Right, like
minimizing
stress concentration.
Those stress concentrations, smoothing out those corners.
Using gentle transitions instead of sharp, abrupt changes. So basically streamlining the design.
Yeah, exactly.
To reduce those stresses.
Exactly.
Okay, what about protecting the surface itself?
So surface treatments can be very effective.
Okay.
So one common approach is polishing.
Okay.
So you polish the surface.
Yeah.
You remove those tiny scratches.
Okay.
Imperfections.
Yeah.
That can act as crack initiation sites.
So it's like giving it a nice, smooth finish.
It's like giving it a nice, smooth, protective layer.
Okay.
Yeah. And then we talked about shot peening.
Right.
You're bombarding the surface.
Yeah, with those little beads.
Yeah. Creating those compressive stresses.
Okay.
And then you have case hardening.
Case hardening.
For steel components.
What's that?
So you're basically diffusing carbon or nitrogen into the surface layer to make it harder, more resistant to fatigue.
So you're kind of like toughening up that outer layer.
Exactly. Okay. And then you have coatings that can be applied.
Protect it from the environment.
To protect it from the environment, yeah.
And that brings us to those environmental factors.
Yes.
That can actually speed up that fatigue process.
So environmental factors can play a huge role.
Like what?
In fatigue. So you have thermal fatigue.
Thermal fatigue?
Yeah. Okay. So that's when a material is subjected to repeated temperature changes.
Okay.
And those temperature changes cause fluctuating thermal stresses.
So like if something heats up and cools down.
Repeatedly?
Repeatedly.
Yeah, that can cause fatigue damage over time.
So it's not just mechanical stresses we have to worry about.
It's thermal stresses as well.
It's the heat.
Yeah.
Right.
And then you have corrosion fatigue.
Corrosion fatigue?
Yeah.
What's that?
So that's basically fatigue in a corrosive environment.
So if you have like a metal component that's exposed to like saltwater
chemicals.
Yeah.
Anything that can cause corrosion. While it's also being subjected to cyclic stresses.
Oh, that's bad news.
That's bad news, yeah.
Okay.
Because the corrosion can create pits and other surface defects.
Right.
And those defects act as stress concentrators.
So it's kind of like weakening the material.
It's weakening the material and then...
And then those stresses.
The stresses deliver the knockout punch.
So it's like a 1-2 punch.
It is a 1-2 punch.
Okay.
And preventing corrosion fatigue often involves a multifaceted approach. You want to protect the material from the corrosive environment.
Okay.
You might want to use more corrosion-resistant materials.
Okay.
And you want to minimize those cyclic stresses as much as possible.
So it's like a combination.
It's a combination approach.
Of strategies.
Yeah.
To combat that corrosion fatigue.
Exactly.
Okay, well, we've covered a lot of ground here.
We've explored the types of stresses that cause fatigue.
Right.
How we test for it.
Yeah.
The mechanisms of crack initiation and propagation.
Yeah.
Those telltale signs of fatigue felt.
The beach marks and striations.
Exactly. And we've discussed a whole arsenal of strategies to prevent or delay fatigue.
From design considerations to surface treatments.
Exactly.
It's been quite a journey through the world of fatigue.
It has been a whirlwind tour.
It has. I think we're ready for our final challenge now.
Okay.
Creep. Creep.
Yeah.
It's like this slow and steady deformation.
It is, yeah.
That happens over time.
It's like watching a glacier carve its way through a mountain.
Yeah, exactly.
Yeah.
It's slow, but it's powerful.
Right, exactly.
It's relentless.
And it can have some pretty significant consequences.
Especially when you think about like structures that operate at high temperatures.
Right, like jet engines and power plants and things like that.
Exactly, yeah. Those are the environments where creep really becomes a major concern.
So the textbook actually describes a classic creep test.
Oh, yeah.
Where you apply a constant load to a specimen at a constant temperature.
And then you just measure the strain or the deformation over time.
All right, so you're basically just watching it.
You're watching it creep.
Creep. Yeah.
And it creates this like characteristic creep curve.
Yeah.
With these 3 distinct stages.
It's like a 3-act play.
It is. It's like the setup, the rising action, and then the climax.
Exactly.
So what happens in each of these stages?
Okay, so the first stage is called primary creep.
Primary creep.
And this is where the creep rate, so the rate at which the material is deforming actually decreases over time.
So it's like the material is kind of resisting.
It's resisting.
At first.
It's trying to hold on to its original shape.
But eventually it's got to give in.
It does eventually, yeah. It can only resist for so long.
Right. And that brings us to the second stage.
Secondary creep.
Secondary creep or steady state creep.
Steady state creep, yeah. This is where the creep rate becomes constant.
So it's like it's found its groove.
It's found its groove, yeah. It's like, okay, I'm just going to deform at this steady pace.
Right. And the strain increases linearly with time.
Exactly.
Oh.
So if you were to plot it on a graph, it would be a straight line.
And this steady state creep rate.
Yeah.
It's really important for engineers, right?
Right, absolutely. Especially for those who are designing components that need to operate reliably for a long time.
Like years or even decades.
Exactly. Yeah. You need to know how fast that material is going to creep.
So you can design around it.
So you can design around it and make sure that it's not going to deform too much over its lifetime.
And then we get to the final stage.
Tertiary creep.
Tertiary creep.
The climax.
The climax.
This is where things start to get a little bit hairy.
Okay.
The creep rate accelerates dramatically.
Oh, no.
Yeah.
And that leads to... Rupture.
Failure.
The material just can't take it anymore.
It can't. It's reached its breaking point.
And this time, to rupture, this rupture lifetime.
Yes.
That's another critical factor for engineers.
Absolutely. They need to know how long that material can withstand those creep conditions.
Before it fails.
Before it fails catastrophically.
It's all about predicting.
Predicting, yeah.
Yeah. How long it's going to last.
Exactly. And understanding the factors that influence that rupture lifetime.
And the textbook mentions that temperature and stress play huge roles.
They're the 2 big players in creep. Temperature and stress.
So the higher the temperature,
the faster the creep.
The faster the creep and the shorter the rupture lifetime.
Exactly.
Okay, and the same goes for stress.
Same for stress. Yeah, higher stresses.
Faster creep.
Faster creep, quicker rupture.
It's like a balancing act.
It is a balancing act, yeah. You're trying to find that sweet spot where the material can withstand the operating conditions.
Without creeping too much.
Without creeping too much and without failing prematurely.
So engineers have come up with some pretty clever ways.
They have, yeah.
To make sense of all this creep data.
Right.
And to try to predict how a material is going to perform.
In the long term.
In the long term.
So one common method is to plot the logarithm of stress versus the logarithm of rupture time for a specific material at different temperatures.
So you're basically creating a visual representation of how those factors are related?
Of how stress, temperature, and rupture time are all interconnected. Okay. And then to extrapolate this data to even longer times.
Yeah, because sometimes you need to know how something's going to perform.
Decades down the road.
50 years from now.
Exactly.
Engineers often use the Larson-Miller parameter.
The Larson-Miller parameter.
What is that?
It's a way to combine temperature and rupture time into a single value that allows you to make those long-term predictions.
So it's like a time machine.
It is like a time machine for materials.
It's pretty cool.
It is pretty cool.
Yeah.
But the textbook also mentions that a material's resistance to creep is influenced by other factors too.
Yeah, there are a lot of things that can affect creep resistance.
Like what?
So things like melting temperature.
Elastic modulus. Grain size.
Okay, so materials with higher melting temperatures and higher elastic moduli tend to be more creep resistant.
They do, because their atoms are more tightly bound together.
So they're less likely to move around.
Exactly, they're less likely to creep.
And what about grain size?
So larger grains actually tend to improve creep resistance.
Which is interesting because usually we want smaller grains.
Right. For other properties, smaller grains are better.
Yeah.
But for creep, it's the opposite.
So it's like a different mechanism.
Different mechanisms, yeah.
At play.
Absolutely.
And then for those really extreme high temperature environments, we have materials that are specifically designed to resist creep.
We have our creep fighting champions.
Like what?
So things like stainless steels, super alloys.
And these materials have?
They often have special alloying elements.
Okay.
And they undergo special processing techniques.
To make them more creep resistant.
To make them more resistant to creep at those high temperatures.
So it's really amazing how much science and engineering
It is, yeah.
Goes into designing materials that can survive.
It's a testament to human ingenuity.
Yeah.
That we can create materials that can withstand those extreme conditions.
So, listener, we've journeyed from that sudden snap of a brittle fracture to the slow and steady creep of metal under high-temperature stress.
We've covered a lot of ground.
We've explored this hidden world of material failure.
Those tiny flaws that can lead to big problems.
Those microscopic battles between stress and resistance.
Absolutely.
And the incredible science that helps us understand
And predict
and prevent these failures.
It's a fascinating field.
It is, and it's so important.
It is, because our lives depend on the reliability of materials.
Yeah.
And the knowledge of those who design and maintain the structures we rely on every day.
So the next time you see a crack in the sidewalk or a rusty old bridge,
or even that frustrating plastic package that just won't open,
remember the intricate world of material failure.
Yeah, think about those microscopic battles.
Between stress and resistance.
Yeah.
And the amazing science that helps us navigate
this complex landscape.
Of materials.
Absolutely.
And if this deep dive has sparked your curiosity, let us know.
We'd love to hear from you.
We're always eager to explore more about the world around us.
Until next time.
Stay curious.